Get it logged in. Most of our questions today are going to come right at the very beginning of the hour. We have a test in here scheduled for Thursday. I believe we're at the point where there's enough seats now in here. We've had enough people withdraw from the course that we can choose wherever we want to sit when we come in here. Maybe we did that last test, I can't remember. But whatever come in, as long as we're every other seat, we come in on Thursday, we'll be just fine. The test will involve organic chemistry, chapter 18. We spent about 2.5 class periods on this. So as far as the material being emphasized on the exam, that material from the organic will probably be emphasized more than any other chapter. Then we went from organic to chapter 12, which was on phase changes and intermolecular forces. We looked a bit at electronegativities and such. And then we went to chapter 13, which we were talking about solutions and solubility last class. Today we'll be dealing with concentrations. As far as what will be provided for you on the exam, always we provided for you a periodic table and conversion sheet. That periodic table and conversion sheet will be provided for you. In addition, there will be like some formulas for molarity and such that will be provided, and your dilution formula, which we'll be going through today, those two, that's what will be provided. So as far as calculations go, the only calculations are the type that we'll be going through today. Everything else, you recall, is stuff that we were naming compounds, and we were in organic chemistry. We had a worksheet that we passed out in here, and I said, if you can do that worksheet with organic chemistry, you should be in pretty good shape. Now that isn't everything, but that's a large portion. And your biggest problem for most students is going to be, can I count carbons? If you can count carbons, you're in good shape. And you have to be able to classify them based on functional groups. So it's an aldehyde, alcohol, and so forth. If you get those two things down, you should be able to complete that worksheet that we passed out in class. The answers for that were on D2L. Beyond that, there are a few other things we talked about in class that weren't on there. For example, looking at a formula and telling whether it's an alkene or alkyne. It's like if you saw a C12H24, what is it? Or if we said that we have an alkene with 12 carbons, how many hydrogens are there? So that type of stuff's in there. We use the terms saturated and unsaturated. We use the terms hydrocarbon. So as long as you know those types of terms, again, you're in good shape. Then chapter 12, as far as electronegativity values go, you do not need to memorize the table of electronegativities. However, I do expect that you know the general trend in electronegativities. And so by general trends, we talked about, for example, if you go down within a group, what happens to electronegativities? They get smaller. As you go across from left to right, the values will get bigger. So if you know that, those general trends, you'll be just fine. If specific values are needed for calculations, they will be provided for you. Shapes, I don't anticipate that you've memorized any shapes other than the shape of a water molecule, which is a bent shape. Other than that, if you need to know the shape of a molecule, it will be drawn on the exam for you. Chapter 13, again, calculation type stuff. We'll be providing you some formulas for molarity and dilutions, stuff that we're going through here today. So any questions that you have on the exam that's coming up? Okay, we have a handout here today. Anybody just come in and not get the handout? Okay. Yep. Pass this down. All right. Anybody else? Okay, so yeah, here we are. We're getting down to just a couple classes left after today. We do need our calculators out today. Anybody need to borrow a calculator or collateral? If you don't have yours out, pull it out right now. We're going to be using these. And I do have sitting up here a demonstration that we will be doing. And right now I am heating this, where is the graph? Here we go. I am heating this water up to its boiling point. Once it begins to boil, I am going to be adding some salt to it, and we'll be observing the effect that the addition of salt has on the temperature of this solution. So with that in mind, let's go ahead and get going here today. I have a couple questions here. First of all, we have two calculations on percentages. And I had meant to put these on your handout today, and I forgot to do that. So let's look at these two. And these will be two questions that show up next in the Socrative app. First one is to calculate the percent by mass concentration of a solution prepared by dissolving 50.0 grams of C6H12O6 in 200 grams of water. And remind you here to be careful. And then next says, what is the concentration, or no, what is the volume of isopropyl alcohol found in a 1 pint bottle of rubbing alcohol that is 70.0% by volume? And V over V here stands for percentage by volume isopropyl alcohol. So I'll give you a chance to go through these. These are the, we should check our answer here on the Socrative app. See how we did. And you recall that a solution, if we have it saturated and add some solute to it, it is still saturated. The only way we can make it supersaturated is if we heat it up above its saturation point, dissolve more in, and then cool it back down. So here are some options for the questions, and these again are next on the Socrative app. These two questions come up. So help out your neighbor. I'll give you about 5, 6, 7 minutes. Go through these calculations, please. I would anticipate that everybody knows how to do percentages. Especially with Cyber Monday yesterday, if you were looking at percent discounts on a pair of shoes or Xbox controller. You know how to calculate percentages. In case you've forgotten, percentage is always the part over the whole times 100. Percent by masses, they get labeled as a percent M over M. Percent by volume, it's labeled as a percent V over V. And then we'll talk about the other two in just a bit. So go ahead and calculate the second one here. First one, we're still waiting for answers on your Socrative app. We've got 20 of you that locked in answers. Okay, let's go ahead and check out the answers here for the first one. We'd like to know what is the percent by mass concentration of a solution prepared by dissolving 50.0 grams in 200 grams of H2O. And then it says be careful. Correct answer is 25.0%. And looks like only 11% of us got it. Who did get it right? And how did you get the 20%? You can admit it. Nobody's going to admit it? I can look you up. So I know who did it. Who got it right? Oh, you just got it right accidentally. How did you get it?
I just added 15,200 and 550.
Right. And why did you add 50 and 200?
That's the whole.
Right. Remember, that percentage is always the part over the whole times 100. So that was the caution here. Be careful. If you are calculating percentage, you need to take the whole amount. So in this case here, we take the 50.0 grams, we divide it by the whole amount. And the whole amount again would be 250.0 grams times 100. And then we wind up with an answer of 20.0% with significant figures. And the labels here, if it's a percentage by mass, which this one is, we label it with a percent M over M. If it's a percent by volume, it's a V over V. And then we'd say it's C6H12O6 for the solute. Any questions on that one? All right, next one here. You are to calculate the volume of a isopropyl alcohol in a 1 pint bottle of rubbing alcohol that is 70% by volume isopropyl alcohol. So what is the volume of isopropyl alcohol? Found in 1 pint. Get our answers locked in. We'll give you about another minute or two. Talk with the neighbor if you need to. And we'll count down. 5, 4, 3, 2, 1. Correct answer here, 331. Great job as a whole. This one, of course, let's write it down very quickly. If we want to find out what 70% is of 473, how do we figure out what 70% is of 473? And multiply it by 0.700 or 0.7 would be good enough. If we do this, we wind up with 331 milliliters as that particular volume. And now the next question we might ask here is this. We'd say, assuming the volumes are additive, which is not always a good assumption, but if we are dealing with room temperature, and in most cases it'll be close, we can ask what volume of water is needed. Or what volume of here we go. What volume of water is in the bottle? And how do we figure that one out? This one should be pretty simple. We're going to subtract. Exactly. We have 473 here. And we'd subtract what? 331. If we subtract these, we wind up with 142 milliliters of water that's in the bottle. And this here, of course, is the 331 milliliters of the isopropyl alcohol. So any questions on either of these two? All right, now there's a third type of percentage that's out there. We have a percent by volume and a percent by mass, but there's also what's called a mass volume percentage. And like to make a distinction between these because when we deal with the percent by mass, these can be in any mass units. These could be, your measurements could be in grams, they could be in kilograms. And even if we had them in pounds, which is a unit of weight, still the ratios in masses are going to be the same. Likewise, in percentage by volumes, these could be any units. These could be milliliters, these could be liters, they could be quarts, gallons. As long as your volume units are the same in the numerator and denominator, we can use any volume units for these. When it comes to mass volume percentage, this is a little bit different. The way that we label this is we'll label it as a percent M over V. Sometimes you'll see it as a percent W over V. And likewise, sometimes for a percent by mass, they'll be shown as a percent by weight. You'll see a percent W over W. And these are ones that I've seen it before, like when students have been carrying around toothpaste. If you look at the percentage of fluoride that's in there, it'll say that the percentage of fluoride is a 0.15% WV of the fluoride ion. And that's just the standard that the American Dental Association has. Or if you have a saline solution, you look at a saline solution, it'll say it contains 0.92%. And I think most of those are labeled as a M over V of sodium chloride. And that is used because those match the concentration of saline that's in your teardrops. So these, though, it is important that we specify the units. And in here, your masses must be in kilograms and your volumes in liters. So they must be kilograms per liter, or they must be milligrams, not milligrams. They'd be grams per milliliter. So the units are important to be specified in here. And the reason why these units are used is because in the case of water, 1 gram of water has a volume of about 1 milliliter. And so that's the reason why a mass volume percentage is used. And so again, other than that, if we go back to the units that are over here, these units that are over here, the units don't matter as long as the units in the numerator and denominator are the same. But for the mass volume percentage, we do need to have very specific units in the numerator and denominator. So from here, we're going to go on to the concentration unit we'll be using the rest of the semester, and that is the units of molarity. And if you've had lab already, you've been working with molarity in lab. And we define molarity like this. We define molarity as being the moles of solute per liter of solution. Whoops, and I see that I forgot my demo. So we got to get back to this. We got to get to the demo before my water all boils away. So let's go back to the demo here. And I think this is the last of our Socrative app questions. And I got to get this down here just a bit. There we go. So our last of the Socrative app questions is this. Sorry about that. With reference to the demo being performed in class today, and I'm doing it right now, when salt is added to boiling water and the solution is returned to boil, the boiling point of the solution is blank compared to the boiling point of pure water. And I'm actually going to demonstrate this. We'll talk about the why later on. I think I got enough salt in there. I do. Looks like it's boiling right around 99 degrees Celsius right now. And go ahead and get your predictions locked in. And we'll count down. 5, 4, 3, 2, 1. And I won't actually show you yet. We'll go ahead and dump this in and see how we do. added in the salt. Getting it to mix around here. We're going to get it back to a boil. And what we should see, what has happened to the boiling point? The boiling point is going up. And I think here I'm just about down to a point where I can hardly get any more to boil. It looks like the boiling point here does in fact increase. And we'll talk about why that is here in just a bit. But we'll see how we did as a prediction. Looks like we kind of had them all over the place, but it is one that is greater than, and we'll talk about why that is here at the end of the hour today. All right, so with this in mind, let's go back to molarity. Molarity is the moles of solute per liter of solution. And if it's moles of solute per liter of solution, what does the word per mean to do mathematically?
Division.
Means to divide. So that means that molarity is equal to moles of solute divided by liters of solution. And if we use an abbreviation, molarity is abbreviated with a capital M. You might remember that moles is abbreviated as MOL, and liters abbreviated with L. So this is what our formula looks like. And you might be wondering then what, like I often hear, what are these things that we've been seeing on our labels throughout the semester? For example, if we saw one with a capital M following it, the way that we read it is like this. We read it as a 1 molar solution. Not 1 molarity, but 1 molar. And it stands for 1 mole per liter. And so if we see something on our bottles, like we did when we worked with the esters lab here a couple weeks back, we saw something like 6M NaOH. This means that we have, and help me out now, it means that we have 6 moles of NaOH per liter of solution. This is what the meaning would be. 6 moles of NaOH per liter of solution. So now, on your handout, we have some questions, and one side is labeled as a worksheet, the other side is in class. So the worksheet side is one that you'll be doing on your own at home. The side that has the, what's that?
One that doesn't have a label?
The one that doesn't have the label is the side that we want. And so find these questions on there. First one says, what is the molarity of 2.50 liters of a solution? And then the second question, I made a mistake. I did some copying and pasting. This one that's in red here, cross out, I believe I put NaOH in there. Not NaOH, I think it was sodium bicarbonate. So cross out sodium bicarbonate and replace it with magnesium nitrate. So again, that's the second question that is on that handout. So again, replace it with magnesium nitrate. So we're going to look at these two here and go through these calculations. We'll start with the first one here. We'd like to know what is the molarity of 2.50 liters of solution that contains 62.6 grams of magnesium nitrate. Well, we need to remember that molarity is equal to moles over liters. So if we remember that molarity is moles over liters, we should then be able to plug this stuff into a formula. First of all, which one are these given? Are we given the moles or are we given the number of liters? Liters. So we can go ahead and put that in, and we have 2.50 liters. Now, as far as the number of moles go, we don't have the number of moles, but what do we have? What do we have? We've got the 62.6 grams of magnesium nitrate. And if we know the number of grams, can we convert this to moles? Yes, we can. So let's go ahead and take our 62.6 grams of magnesium nitrate, and let's convert this to moles of magnesium nitrate. Now this is where we need to go back to some stuff that we did earlier this semester. Let's assume now that you know how to calculate the correct values. What do we need to find? Molar mass. So let's go ahead and find that molar mass. To find the molar mass, we need to go back to our periodic tables. So we'll put in a periodic table here. We need, and anybody need a copy of the periodic table? Someone here somewhere. There we go. Anybody need a fresh copy of the periodic table? Okay. This one down. There. Yeah. Anybody else need one? Remember, you can never have too many periodic tables. Well, you can, but just pretend you can't. So, let's go ahead and look at magnesium. We have one magnesium. How many nitrogens in our formula? 2. And how many oxygens? 6. So let's add up. One magnesium at 24.31 plus 2 nitrogens at 14.01 and 6 oxygens at 16.00. Check my math, I'm coming up with 148.33. Okay. So now if we do the conversion, where does the 148.33 go? In the bottom. So that tells us there's 148.33 grams of the magnesium nitrate for every 1 mole of magnesium nitrate. And we do this so grams of magnesium nitrate cancel out. And after we do our calculation, we'll take 62.6, divide that by the 148.33, and we wind up with 0.4220 moles. And I always like to take an extra digit along for the ride to prevent rounding errors. We get 0.4220 moles of the magnesium nitrate. Well, then if we want to find the molarity, we now know the number of moles. We can go ahead and plug this in right here. We've got 0.4220 moles of the magnesium nitrate. Divide that by the 2.50 liters. And we wind up with an answer of 0. Now, how many sig figs should be in the answer? 3. So we'd round this off to 0.169. The label on this is going to be moles of magnesium nitrate per liter, until we remember that every time we see a mole per liter, we substitute that with big M right here, and we then say that the concentration is 0.169 molar magnesium nitrate. So any questions on this particular calculation? Okay, next up, we'd like to know what mass of magnesium nitrate is needed to prepare 250.0 milliliters of 0.200 molar magnesium nitrate. Remember, there's an error in this problem the way it is in your handout. This one that's in there, get rid of the sodium bicarbonate, replace it with the magnesium nitrate. Now in this one, couple key things. First of all, we talked about how the word per means to divide. If we see two quantities separated by the word of, that means that we are going to not divide. We're going to multiply. So two quantities separated by the word of means we multiply them together. In fact, if you go back to the first page, we see that we had two quantities separated by the word of. And in this case here, we multiplied them together as well. So again, two quantities separated by the word of means we're going to multiply them together. Now, we start this one out by taking the 250.0 milliliters of 0.200 molar magnesium nitrate. At this point, we can't do anything with the units because this is milliliters, this is molarity. We're going to get a mass out of here. We're not going to get anything for the mass. So we need to remember how these things are defined. Big M here stands for moles per liter. So again, we are making the substitution where big M stands for moles per liter. Well, now this still isn't going to cancel out the way that we'd expect because this is milliliters, this is liters. So that means we need to take our milliliters here and convert it to liters. So with this one, and I'll put this one in purple, this one here, we need to convert this to liters. And you might remember, we'll go ahead and convert this down below here. There we go. We'll take the 250.0 milliliters. We need to convert it into liters. We then need a conversion between milliliters and liters. And there's 1,000. Where does the 1,000 go? It goes on the bottom. And remember, the way that that works is that the larger number is attached to the smaller unit, and the smaller number attached to the larger unit. So in case you have trouble with it, remembering which way it goes, just remember larger number with the smaller unit, smaller number with the larger unit always works. And so if we divide this by 1,000, we wind up with 0.2500 liters. So we come back up here and we'll replace this with 0.2500 liters. And again, the whole reason for doing this was we want to make sure that what happens?
Cancels.
Units cancel. That's where we started this whole course was to analyze our dimensions. We started with dimensional analysis. So liters cancels out. Of course, at this point now, our units would be moles. We're not trying to get to moles, we're trying to get to mass. And mass is measured in which units?
Grams.
Grams. So in other words, we want to know how many grams. So we should be able to take the number of moles here and convert it to grams. And how do we convert from moles to grams? Use the molar mass. And we already calculated that right up above. We calculated it right up here. So if we want to put this in, on the bottom we'd put in moles, specifically 1 mole of magnesium nitrate. On the top we'd put in 148.33 grams of the magnesium nitrate. Moles of magnesium nitrate cancel out. And then we should be able to calculate the answer. I'm going to slide this over just a bit. So to calculate our answer, we have 0.25. We'll multiply that by 0.2 and multiply again by 148.33. Once we get our answer, we need to ask how many significant figures. And how many should we have? Should be 3, because the 0.200 has 3 significant figures. So we'd round off our answer to be 7.42. The label is grams of the magnesium nitrate as the answer. Okay, then the next part of the question. Oh, first of all, any questions on this piece? Okay, then the next piece is we'd like to describe how the solution would be prepared. And now I forgot to bring out my volumetric flask, so I'm going to grab one here real quick. See if you can talk over with a neighbor to decide how much of the different stuff we're going to use. So how much water, how much magnesium nitrate. We want to describe how the solution here is going to be prepared. And those of you that were in lab yesterday, what do we call these devices here? They're called the volumetric flasks. These are called the volumetric flasks. So the volumetric flasks come in a variety of different sizes. The one that we used in lab yesterday was this size right here, a 100 milliliter volumetric flask. But again, they do come in various sizes. This is a 25 milliliter volumetric flask. This one here is a 1 liter volumetric flask, and I've seen them come as large as 5 liters. And I've seen them come as small as 5 milliliters. This one here is 25, so there's a baby size that's out there as well. And of course, you used these devices in lab before. We did them earlier this semester, but we also used them yesterday. These are called pipettes. So, if we want to do this particular one, which piece of glassware are we going to need? Which piece of glassware are we going to need? Are we going to need pipettes? Are we going to need volumetric flasks, or will we need graduated cylinder? We need the volumetric flask, and specifically we need a volumetric flask that measures 250 milliliters. So if we're going to use this volumetric flask, then we go back and we see how much of the various things that we will need. So if we want to make this solution, in the end, how much volume are we going to need to make? 250 milliliters. And how much stuff are we going to need? Well, here's the stuff that we calculated. We need 7.42 grams of magnesium nitrate. So if you want to describe how the solution would be prepared, and this is what we did in lab yesterday, we might do something like this. We might say we would place 7.42 grams of magnesium nitrate into specifically a 250 milliliter volumetric flask. And again, if you were in lab yesterday, then what are we going to do to it? Add what? Add water. And we're going to add water, and not all the way up to the line, but we're going to add some water and then mix to dissolve the solid. And once the solid is dissolved, then what do? Fill it up to the line. So then we add water to the line on the neck. And we're still not quite finished. One step left, and that is we can't just bring it up to here, it's still not there. What's next? We have enough water, But what's wrong with the solution? What do you need to do?
Shake
Yeah, you need to mix it thoroughly. So we need to shake it or mix thoroughly. So these are the steps we go through in making this particular solution. We place a 7.42 grams of magnesium nitrate into the volumetric flask. We add water, mix to dissolve. Then we add water to the line on the neck, and then we mix thoroughly. Now, if we don't have a volumetric flask, we could use a graduated cylinder. If we use a graduated cylinder, the way it would work in a graduated cylinder is that we would go ahead and put in our solid, and then what?
and more water.
Add water. Once we add the water, we mix it up thoroughly, and then we add water up to the
Correct.
250 milliliter line on there, and once we add it up to the 250 milliliter line, then we mix thoroughly, and we have our solution. If, however, we do have a volumetric flask available that measures the correct volume, we would use the volumetric flask over the graduated cylinder, because these here are more precise than the graduated cylinders. We do not use beakers to make these, because if you've ever looked at the beakers, they will say right on there, like this says plus or minus 5%. These here are only meant to measure approximate volumes. And so these would be the very last choice. These are not the best choice, but if it's all that we have available, the graduated cylinders are intended to be measured more precisely than the beakers. And then if we have a volumetric flask available, these are the best choices that we'd use. Now the other thing that I like to say here, how many have ever made Kool-Aid before? Okay, now if you make Kool-Aid, you look at the direction on the packages, and it will say something like, makes 2 quarts, or that's what it says out on the label. And so when you mix it together, you dump in your Kool-Aid, you dump in your sugar, and then the amount of water you add is enough water to make 2 quarts of solution. You don't dump in 2 quarts of water, you add enough water to make 2 quarts. Because what happens if you dump in 2 quarts of water? Well, it won't splash, but how's it going to taste? Watered down, right. Because in the end, how much solution are you going to have? If you add in 2 quarts on top of your sugar, you're going to have 2 quarts plus whatever sugar or whatever that you dumped in. And so it's going to be diluted down. So if you think about it, I like to call this the Kool-Aid rule. Just think of it like the Kool-Aid rule. Because when you make Kool-Aid, again, the package says it makes 2 quarts. It doesn't say that you add 2 quarts of water. It says that you make 2 quarts of Kool-Aid. And so that was one of those things when I think back to my mom making Kool-Aid, you know, whatever it is, 30, 40, 50 years ago. Her Kool-Aid is always watered down, and that's because she always added in 2 quarts of water. It wasn't until I became a chemist that I had to point out the flaws to my mom. All right, so any questions? Now, a very simple way you could do this is like this. We could say that we could add 7.42 grams of magnesium nitrate to enough water to make 250.0 milliliters of solution. So that would be an abbreviated way of saying it without being specific as to which piece of glassware you use. But what would be wrong to say is to add 250 milliliters of water to 7.42 grams of magnesium nitrate, because again you wind up with more than 250 milliliters of solution. Okay, any questions on these? Okay, now you remember that our formula for molarity is equal to moles over liters. Some of you I know are a little bit algebra challenged. So if you're algebra challenged, here's, you might remember when we did the density pi way back when. We also have a molarity pie. It looks like this. We put moles up on top and molarity in liters on the bottom. And then if we want to solve for any one of these, we just cover up the one that we want to solve. So if we want molarity, molarity is moles over liters. We want to find the number of liters. That tells us we take the moles divided by molarity. If we want the number of moles, side by side tells us we take molarity times liters. So the molarity pie works very similar to the way the density pie worked earlier this semester. All right, next up, we're going to look at dilutions. And we look at dilutions. Your text has a dilution formula which says M1V1 is equal to M2V2. And in this formula, M here stands for molarity. But there's a more general dilution formula that you may use. A more general one looks like this. C1V1 equals C2V2. And I prefer to use this latter form because it's a more general form. And in here, we say that C stands for concentration. V stands for volume. A subscript of 1 stands for before or beginning, right? Before dilution, or it's the beginning one. And a subscript of 2 stands for the second one, that is after dilution, or the end value. And of course, these should look very similar to the Boyle's law we did when we dealt with gas laws back in chapter 10 or 11, whatever that was.
Would this be with the keeping temperature constant?
These we don't need to, well, we should keep temperature constant, but that would be the general assumption, yes. They work a little bit different than gas laws, simply because of gas laws, temperature has a great effect on the expansion or contraction of gases. And it has some effect on solids and liquids, but very minimal. But yes, constant temperature should still be in play. So we have a couple more questions here on our handout. And this here is question number 3. And it says, what is the concentration of a solution prepared by diluting 10.00 milliliters of a 20.0 mass volume glucose solution to a final volume of 10 milliliters? So a couple key things here. First of all, this is a dilution problem, which we gather by saying we're diluting it. So if we look at our dilution formula, C1V1 is equal to C2V2. Another hint that we have in here is we see two quantities separated by the word of, which means that we're probably going to be doing what with those two numbers? We're going to be multiplying those numbers. Remember that the word of means to multiply. So then we need to go through and label our values. What is it we're looking for in this problem? We're looking for the concentration. Are we looking for the concentration at the end or at the beginning? At the end. So we are looking for C2. So that means that this amount here must be C1. So again, I like to go through and label these right in the problem. The 10 milliliters, this is going to be V1, and the 200 milliliters is going to be V2. Very easy way to remember this. When you dilute something, you start with a volume that is small. You wind up with one that is large. And if you're dealing with the concentrations, you start with the concentration that is big, and you wind up with a concentration that is small. So whenever you dilute something, if you're not sure how to label it, remember that you start with small volumes. If you dilute it, you wind up with a bigger volume. Concentrations start large, and at the end the concentration should be smaller. So we're going to solve this one for C2. That means we take each side and divide it by V2. V2 cancels out. Tells us that C2 is equal to C1 times V1 all over V2. And then we substitute in our values. Substituting them in, we have 20.0% mass volume glucose. Volume is 10.00 milliliters, and we're going to divide this by 200.0 milliliters. Now the other beauty of the dilution formula is this. We do not need to convert our units as long as the units in the numerator and denominator are the same. So this one here being in milliliters is fine because milliliters over milliliters will cancel out. And then to calculate the answer, looks like we're going to take 20 times 100. Not 100, that is times 10, 20 times 10, and we'll divide that by 200. And we wind up with a value of 1. And how many significant figures should that 1 have? 3. So it's going to be 1.00%. And then the label is going to be M over V, C6, H12O6. And that there is the solution. Yes?
So we use 20 and not 0.2.
And we don't need to convert it to 0.2 because in the end, if we're trying to find a concentration, this concentration at the end is also a percentage. So if you did convert this to 0.2, then you have to remember to convert it back to percentage here at the end. So as long as we have this as a percentage, and we're looking for a percentage, we keep this as 20 throughout the calculation. Anybody else? Good question. Okay, next one. We'd like to know what volume of 6 molar K2CO3 is needed to prepare 500 milliliters of 0.50 molar K2CO3. And then, assuming that the volumes are additive, what volume of water is needed? So let's go through this particular one and label them just like before. What is it we're looking for in this problem? We're looking for volume. Are we looking for the volume of the stuff we're starting with or the volume we're ending with? What we're starting with. Because we're ending with 500 milliliters. We're preparing 500, so that means we need to know how much of the starting stuff we need. So we're looking for V1. And the 500 milliliters is what we're ending with, which is the V2. 6 molar. This is going to be
M1.
M1. And this here is going to be M2. Now, in case you've forgotten, again, we see two quantities separated by the word of. Two quantities separated by the word of means we're going to multiply these together. So if we set this up into a formula, we have M1 times V1 is equal to M2 times V2. Since we're solving for V1, we have to divide each side by M1. M1 cancels out. So we have M2, which is the 0.50 molar K2CO3. We're multiplying that by the 500 milliliters. And we're dividing that by the 6.0 molar K2CO3. And at this point, to get the answer, what happens? Molarities will cancel out. We then take 0.5, multiply that by 500, and we divide that by 6. And how many significant figures should be in the answer?
2.
2. And that's because we have 0.50 has 2 sig figs, The 6.00 has 2 sig figs. So 2 sig figs in the answer we have 42 milliliters. And this will be the 42 milliliters of the 6.0 molar K2CO3. And then the next question reads, assuming the volumes are additive, what volume of water is needed? So how do we find this one? We subtract. And what do we subtract in these? 500 minus 42. And we wind up with 458 milliliters of the H2O would be needed. So if we wanted to make 500 milliliters of solution, we need 42 milliliters of the 6 molar potassium carbonate. We added 458 milliliters of water, and we get our 500 milliliters of solution. So this kind of takes us through the calculations that we need for this chapter and for this exam. Any questions on anything here from dilutions or molarity? Anything on dilutions or molarity? And then again, it's always a good check. We said that if we have two quantities separated by the word of, that meant we were going to multiply them together. Did we in fact multiply these two together?
Yes.
We did. And back in the previous problem, we said if we have two quantities separated by the word of, that meant we were going to multiply them together. Did we multiply them together?
Yes.
Yes, we did. So that's always a good check to do if you're kind of uncertain about the math, is analyze your words of and per. Remember that of means to multiply, per means to divide. And so going back to your definitions is a good way to, I guess, give yourself some confidence you're doing these correctly. All right, we're just about here. We got one more thing that we need to cover before our exam on Thursday, and that is colligative properties. Now, colligative properties is something that we've actually used this term already this semester. Anybody remember where it was used? We used it in a lab. The lab we used it on might have looked something like this. And I'm going to go ahead and do a new file. So let's do a new experiment. No, I don't want to do that. Let's do this. I'm going to start this at about 10. And we'll put this one on the bottom here as negative 10. And now my ice is not crushed, but what I'm going to do here is I'm going to go ahead and we'll store that latest run. There we go. I did bring in some ice here today, and I'm going to pour the water off of here. And you may remember in one of your labs, you crushed up the ice, and then we were measuring the temperature of ice and water mixture. And there we go. What temperature should we wind up with once we wind up with 0 with ice and water mixture? With any luck, there it's going to level off right at 0. And we see now that temperature is relatively constant. And then in your lab, what you did is you added some salt to the mixture. And once we add salt, what happens to the temp? It goes down. So we dump in a bunch of salt here. And once we add in the salt, we can see that temperature does in fact go down. And of course, if we crush up that ice a little more, then we see that the temperature goes down even more. And this is one of the colligative properties we looked at earlier this semester in the lab. And what is one application of this?
Salting roads.
Salting the roads, exactly. And when we salt the roads, the whole purpose of adding salt onto the roads is to decrease the freezing point. We want the water to freeze at a lower temperature. And so many of us got this prediction wrong in the lab because we were thinking that, oh, well, we put it on there and it melts it because it's warming it up. Well, it's not warming it up. It's lowering the freezing point. And by lowering the freezing point, that allows the water to freeze at a lower temperature. So we say that colligative properties are these. We say that these are properties of solutions. These are properties of solutions that depend only on the concentration of solute particles and not on their identity. So again, these are properties of solutions that depend only on the concentration of solute particles and not on their identity. And you recall one of the things that you did in that lab was that you didn't just use salt, but you used salt, you used sugar, you used ice melt. For my online students, I had them use baking soda, and as long as it dissolves in there, it has that same effect. In your cars, instead of using salt in your radiator, you use antifreeze. It's the same thing. You add the antifreeze to your radiators to cause it to freeze at a lower temperature to prevent your radiator from freezing up. And so the first of these is what we call freezing point depression. It doesn't matter which solute we use, as long as we dissolve a solute in a solvent, the freezing point is going to go down. And just like we saw with the first trial we did here today, what happened when we added a solute to the water? The boiling point went up. And so we call this one boiling point elevation. Now, a very common misconception of boiling point elevation is if you're doing some cooking at home, you add in some salt into your pot of water, and I'll hear students say, oh, well, yeah, my mom used to add salt to the boiling water when she was making pasta to increase the boiling point. Well, typically if you add salt to the water to boil your pasta, how much salt do you add?
Not a lot.
Not a lot, like a pinch of salt. And you put that pinch in a big pot, oh, not that big maybe, but you put it in a big pot of water. If you notice when I made this here, I had a small amount of water and I added in a huge amount of salt. And the boiling point went up just a little bit. Okay, so this whole notion of adding salt to the water to make it boil fast or boil at a higher temperature, that's a wives' tale. That's just not true. It's just added for a little flavor or maybe just for appearance, but that's all. It doesn't do anything for you. Okay, you have to add in a whole bunch of salt like we saw here, a whole bunch of solute to cause that boiling point to go up even a small amount. But we do use this stuff in one way. Anybody know one way that we do use boiling point elevation? By adding a solute, causing the boiling point to go up.
Reactors.
We use it in our cars as well. That antifreeze that we add to it in the winter to prevent it from freezing, in the summer prevents it from overheating or boiling over. When we sell the product in the winter, we call it antifreeze, and we sell that same product in the summer, you hear it referred to as coolant. But it's the same stuff. Okay? Coolant and antifreeze, it's the same stuff. We just, depending upon the season, just give it different names. So again, that stuff we add to our radiators prevents it from boiling over in the summer, prevents it from freezing up in the winter. Another property is vapor pressure depression. And we're not going to talk about this one at all, but I just want to list it because it is one of the four. And then the last one we're going to look at is osmotic pressure elevation. osmotic pressure elevation. And I'm going to relate it now to the extra credit lab that those of you have done. So this is your last call. Anybody need to turn in your extra credit lab? After this point, you can't. All right, here's what was done in the extra credit lab. 3-day lab. Day 1 looked like this. In day 1, you took a raw egg and a shell and you put that into vinegar. So when we put the egg into the vinegar, and it's a raw egg and the shell in the vinegar, what happens on day 1, do you think? Even if you didn't do it? Shell did what? Dissolves, exactly. The shell dissolves. For those that did it, the shell dissolves. That was the first thing. So basically then what you're left with is an egg inside of a membrane, and that then was transferred in day 2 to either corn syrup or honey or a concentrated sugar solution. And so when that egg was transferred on day 2 into the corn syrup, then what happened to the egg when it was transferred into the corn syrup? It collapsed, exactly. So it kind of looked like, I've often heard it described as kind of like a deflated football. Something like this. And then on day 3, that egg was taken out of here and was transferred into some water. And when it was transferred into the water, what happened to it? It expanded. And that egg got really big. Okay? So something like this. And this has to do with the concept that we call osmosis. Now, when I was in biology, and I took many, many biology classes over the years, the way that biologists define osmosis really bothered me as a chemist, because the way that and see if this is the way they still define it. They talked about osmosis as the movement of water through a semi-permeable membrane from areas of higher concentration to areas of lower concentration. Is that the way they still define it?
Yes.
Okay. Now, what I don't like about that is when they talk about concentration, they're talking about the concentration of water. And when chemists talk about concentration, we never talk about the concentration of water. We're always talking about the concentration of the solutes. So chemists would define it like this. We say it is the movement of water through a semi-permeable membrane from areas of low solute concentration to areas of high solute concentration. And if we went back then and looked at what happened in these eggs, well, first of all, if we talk about semi-permeable, if it's semi-permeable, let's go back to what permeable means. If we said something is permeable, that means it allows things to pass through indiscriminately. Permeable just means it allows things to pass through. If it's semi-permeable, that means it allows some things to pass and not other things. So like a coffee filter, something that's semi-permeable. It allows like the water and flavorful stuff to go behind, but it doesn't allow the coffee grounds to pass through. Okay, that would be an example of something that's semi-permeable. Allows some things to pass and not others. So it turns out that water molecules are really small. And if we wanted to describe what happens here in this egg, what's happened is that in this egg, the water molecules have moved out because inside the egg it had a low solute concentration, and so that water was moving out to areas where the solutes were more concentrated, which was in the corn syrup. And in day 3, we do not need to pack up yet, please. In day 3, what happens is that the water was moving into the egg because the inside of the egg had a greater solute concentration and the water needed to move into the egg. The whole idea is to balance those solute concentrations. Now, how many of you are planning health-related professions, either doctor, nurse, or anything like that? Okay. Now, if you're planning a health-related profession, let's say, for example, you want to give someone an injection or an IV. Let's talk about an IV. Maybe say you had IVs before, and you're in a lot of pain. You're in a lot of pain. Probably the number one drug that they administer in the hospital is morphine. Okay. Now, morphine is not something you're going to put in like a pound of morphine into you, because you put a pound of morphine into you, you're going to kill you. Even if you put in a couple grams of morphine into you, it's probably going to kill you. Okay, so the amount of morphine that you need is really small. So you want to put that morphine into some water. But now if you inject that water, that morphine that's in the water, it's in your IV bag, into the body, what's going to happen is that that water is going to run into, think of this egg now, not as an egg, but as a red blood cell. What's going to happen is that water is going to want to rush into those cells, and the cells are going to burst. Okay, so if you want to administer that morphine, instead of putting it into water, you put it into
A plasma?
well, plasma is one thing, but you'd probably either put it into a sugar solution or a salt solution. You put it into a salt solution, which they call saline in the hospital, if you need to get hydrated, okay? And they would put it into a sugar solution, which they call dextrose or glucose, if you need nutrients. Like if you can't eat, you need to get some nutrients, so put it in one or the other. Okay? They put it into the saline, they're going to put it into a 0.92% solution. You heard me refer to that earlier, and that matches the blood plasma concentration. Or if they put in a sugar, they'll put it into 5.5% solution. Whole idea is that we don't want water moving into cells, we don't want water moving out of the cells. We want it to be balanced. And so that type of solution is called an isotonic solution. And that is where we run out of time here today, but yeah. We will see you then in here on Thursday for exam, any seating, every other seat. Office hours available.